Take that dead phone sitting in your drawer, with a cracked screen and a battery that refuses to charge. As a working piece of technology, it has practically zero value. But mixed inside that glass and plastic is real 24-karat gold. You won't find a hidden coin. The gold exists in coatings so extremely thin, sitting on electrical contacts and printed circuit boards, that you might never recognize them as gold at all. A single typical device contains only a few hundredths of a gram of this metal. Because that quantity is microscopic, recovering gold from one phone makes little economic sense. The real achievement we're looking at starts not with chemistry, but with a massive logistical problem. A factory cannot recover metal from a device that never reaches it. Developed recycling markets solve this through a vast intake network, pulling in unwanted electronics through retailer take-back programs, municipal collection points, and corporate trade-in schemes. Everything entering that network arrives in a totally different condition. So the first major system evaluates a simple economic choice: whether the device retains more value as a functioning phone or as a pile of raw materials. If a phone can be securely erased, repaired, refurbished, or stripped for reusable components, it is diverted entirely away from material recycling. Once a device is broken apart, its highest value function is gone forever. Destroying it to extract base materials is the absolute final option, reserved only for electronics that can no longer be reused economically. For the phones that do move deeper into the recovery chain, the factory faces an immediate physical hazard: the lithium-ion battery packed inside almost every modern device. You cannot drop a complete phone into a powerful industrial shredder. If that battery is bent, punctured, or crushed, it short-circuits and releases intense heat, easily igniting a collection vehicle or the entire industrial waste stream. Therefore, the first step is physical extraction. Workers, or specialized systems, open the housing to separate the battery, the screen, and the casing. This isolates the true target, the highly engineered printed circuit board where the precious metals actually sit. At this point, we still only have a fraction of a gram of gold per board. The system functions economically only when thousands of these stripped circuit boards are pooled together into a highly concentrated industrial stream. Facilities then break these electronic assemblies down into smaller pieces. Magnets pull out iron and steel, air separation blows away lighter plastics, and density equipment divides remaining metals. None of these machines produces pure gold. Their entirely different job is solving the problem of dilution. Every kilogram of plastic or steel they systematically strip away is mass that does not have to be chemically processed later. Before refining begins, the factory has to determine exactly what it received. Electronic scrap is highly irregular. One batch might be rich in gold-plated contacts, while another has almost none. The facility must take carefully controlled samples and analyze it, reducing tons of uneven material into precise data to control the economics of the entire plant. With the composition known, the deepest separation starts. In large integrated refineries, this prepared scrap enters a smelter. The extreme temperature breaks down the physical structure, burning off organic materials like plastics and forcing unwanted minerals into a waste slag. What remains is a dense metallic mix, primarily copper, which collects the precious metals. Refineries use an electrochemical process called electrowinning to separate them. By running electricity through a dissolved solution, they pull the copper onto solid surfaces, leaving behind a highly concentrated precious metal residue. Other, newer facilities take an entirely different chemical route. In places like South Wales, factories use selective solutions operating at room temperature. Instead of melting the board, they expose the material to specialized chemistry, pulling targeted gold directly into a liquid in minutes. But whether it comes from a copper-rich residue or a chemical liquid, the dispersed gold doesn't look like gold yet. Through controlled precipitation and filtering, that dissolved material is forced back into a solid. It emerges as a dark, unremarkable powder or sludge. Only after that dark sludge is heated beyond its melting point and heavily purified does it take shape. This immense industrial chain successfully reverses the complexity of a modern smartphone back into a fundamental element: pure 24-karat gold, testing at a fineness of 999.9. Yet gold represents only a tiny fraction of the recovered phone. A credible recovery system cannot just chase the precious metals and ignore the rest. Every output, the immense quantities of copper, aluminum, and steel, must be separated and returned to manufacturing. Managing all of these different outputs safely requires heavy, invisible infrastructure. Beyond the shredders and furnaces, these plants run on constant ventilation, precise wastewater treatment, and rigorous material tracking. You can extract gold from electronics using aggressive chemicals in a crude, informal setup, but doing it repeatedly at scale, without burning plastics in the open or releasing contaminated liquids, requires a highly regulated operation that actively contains its hazardous residues. Without this strict ecosystem, pulling those microscopic amounts of gold would inevitably create an environmental and toxic disaster far larger than the waste problem it attempts to solve. And we desperately need that infrastructure to scale, because the world currently generates tens of millions of tons of electronic waste every single year. Imagine more than 1 million fully loaded heavy cargo trucks packed entirely with discarded computers, phones, and appliances. Placed bumper to bumper, that single line of vehicles would stretch entirely around the planet. The tragic reality is that only a fraction of this mountain is formally collected and recycled. The rest, holding billions of dollars in industrial and precious metals, simply disappears into household garbage bags or undocumented networks. Think back to the physical journey of that dead phone sitting in your drawer. Through this highly controlled sequence, the complex device has vanished completely. In its place are distinct, cleanly separated streams of copper, glass, plastics, and pure battery minerals. A discarded phone is not a miniature gold mine on its own. The gold is too thin, too scattered, and too deeply mixed to matter individually. The true marvel is the hidden industrial machine, capable of diving into absolute chaos, capturing an invisible trace of metal, and calmly returning it to a state of perfect purity.